Welcome to this new video on correlation, linear regression, and ANOVA. Okay, so for today, what I'd like to go over next is I'd like to talk a little bit about what inferential statistics are. Then I'd like to talk a little bit about the general linear model because this is going to apply to correlation, linear regression, and ANOVA. Next, we're going to talk a little bit about what you need to look for, and then we'll go through some basic data visualization of inferential statistics in ggplot2, which we're going to spend a lot more time with as this course goes further. Okay, so in terms of what what inferential statistics are, is inferential statistics are a branch of statistics that allow us to infer things from our data. Descriptive statistics only allow us to allow us to visualize or look at the data, but they don't necessarily allow us to tell group differences, be able to understand whether there's a relationship between two variables or things of that nature. In inferential statistics, we're more interested in trying to understand what it means for there to be a relationship between a variable, or whether a variable is different from zero, or anything like that. So most of what you see in a research paper is going to be inferential statistics in nature. So in terms of what inferential statistics are, let's go ahead and let's talk a little bit about the general linear model. So the general linear model is something that encompasses most of the statistics that we conduct within hypothesis testing based statistics. So whenever you see most research papers, you'll be typically looking at something that involves the general linear model. And this involves multiple different branches of statistics, and it can include things like structural equation modeling, things like regression analyses, which encompasses ANOVA, correlation, and then also linear regression. And then it also, and both of these branches of statistics also fall under something called canonical correlation, and everything falls under the general linear model. Now, the reason that I mention this is to point out that the mathematics are generally speaking the same for all of these different branches of statistics, and we're just looking at different ways to be able to explore how we can use these data in different manners. So when we talk about what regression analyses entail, it entails a number of different types of analyses. It includes things like the chi-square analysis, which is a way that we can tell differences between groups in terms of categorical variables. It can include things like correlation, so Pearson's R, for instance, a Spearman correlation, and things like that. It can include things like ANOVA and ANCOVA, so analysis of variance, and then also the analysis of covariance, which is a special case of ANOVA that allows us to covary or adjust for different variables when we're looking at differences between groups. It also allows us to look at things like linear regression as well, and then it includes things, basic tests that we might run, like the t-test, or something of that manner. So all of these things fall under linear regression, or under regression type analyses. And so the assumptions of regression type analyses are very broad, but we'll try and go through these as quickly and as succinctly as possible. The assumptions of regression analyses include linearity, independence, normality, and equivariance, sometimes referred to as homoscedasticity. So what do these things mean in terms of what we're looking for? Well, broadly, the regression model is linear in its parameters. So what that means is that it is going to be something that is additive in terms of the individual parameters themselves. So that means that when we think about that traditional model of y equals mx plus b, that each individual parameter that we are including is going to be an added part of the model. What it doesn't mean is it means that we cannot sum the beta coefficients in terms of it being multiplicative. So for instance, you can't have you should not be looking at something wherein we are timesing multiple parts of the model in a multiplicative manner. So, for instance, this model at the very bottom is squaring one term, and that would be a polynomial model, something that's nonlinear in nature. So, when we talk about regression, we're talking about something that is very linear in fashion. It's additive. It's one individual term added to the next and the next and the next. Now, in terms of the assumption of independence, what this means is that each observation is independent of each other. That is, that it's not influenced by a previous observation. So, a good example of something that is not going to be independent in nature is something like height. So, for instance, if I were to just measure one person's height over the course of their lifetime, I would note that each individual height that is taken is going to be influenced by the previous one. So, as somebody ages, then we would expect that the relationship between age and height is going to be positive in nature, but that's really just because one person, as they start to age, it's being influenced because it's coming from the same subject over time. We would expect the same thing to happen in terms of independence as well. We should not be seeing that a previous observation is going to be influenced by the next, nor is it going to be influenced by another one. And we can test this by looking at residuals plots of the residuals versus the fitted model itself. And we should see that the residuals in nature should be relatively independent of each other. They shouldn't be all lining up one over another. In terms of normality, we're expecting that the residual errors are normally distributed. That means that the residual errors, or the error of the model from what we actually see versus what we would expect, is going to be something that is going to be the same across the model. We shouldn't see that at the tail ends of the model that there are residuals that are really, really, really far off from what we would expect from the standardized residuals. And so when we do something like a QQ plot, what we would want is to see that these last couple observations are going to be at least somewhat close to the line that we've developed here. So we don't want to see this wavy shape that's going way off the model. We don't want to see a U shape. We just want to see this somewhat sticking to the line throughout the course of all our observations. And then lastly, equivariance or homoscedasticity. And what this refers to is that the residuals should not increase with fitted values of the response variable. So we already talked a little bit about how when we talk about independence, we would expect each individual observation to be independent of the previous one or of the next one. But what we should also see is we should not see that the variance of residuals should not increase or decrease with fitted values of the response variable. And so we shouldn't see a fanning effect in terms of variables. So right here, you can kind of see that the spread of the data starts to increase as the value starts to improve over time. And we would want to see that there would be a straight line sort of in terms of this plot over here. So really, you don't want to see a fanning effect in terms of your data. You don't want to see any narrowing in terms of your data. You would like to see the values to be the same across time in terms of how they vary across like an individual variable of interest. So in summary, what we've talked about here, and this is a very, very simple, basic discussion of these concepts, and you can get into a lot more detail if you were so inclined, is we are interested in trying to make sure that the most fundamental understanding of statistics is rooted in the same mathematics. We're using the same math regardless of the different types of analyses that we're running, especially when it comes to regression analyses. This means that how you write your R code is going to be basically the same for many common types of analyses, and this especially applies to ANOVA, ANCOVA, and linear regression. Now, it's important to also recognize that most inferential statistics are based on assumptions about the data, which we need to check, and we need to be sure about those assumptions before we can accurately suggest how our data might be related to each other, or there might be group differences between variables of interest. Okay, so with that said, let's just go ahead and let's get right into it. All right, so next, just make sure that you have your R Studio open, and we're going to go ahead and we're going to load those test data again. And we're going to start out by just working through some correlations. So again, we'll just use the same code that we've developed throughout this, using again the path name for where your data are located. And so once those data are located, let's just go ahead and rename those variables just so we're all on the same page. Okay, so for right now, we're going to start out with just going through some correlations. So a correlation, as you're probably aware, is just when bivariate correlation is when we're just trying to plot one variable against another variable in order to look at an association between one variable and another variable. So, for instance, if we were looking at height and weight, we would expect there to be a positive correlation between height and weight. So people who are taller weigh more, and we could also say that people who weigh more are generally taller, and that would be what we'd be looking for in a basic correlation. So in order to do correlations in R, there are several different ways that we can do this, but we're going to start out with just the most simplistic one, wherein we can type in core, and then we will just go ahead and we're going to run a basic correlation looking at age and ADA's COG score. And ADA's COG, just as a reminder, a lower score is going to be indicative of better cognitive performance. Okay, so we just need to go ahead and first load the baseline data that we had previously. So let's just go ahead and we're going to create this new data set called baseline, and we'll subset it, and we're just going to go ahead and take data 2 and then time point equals, remember 2 equal signs 2. Oh, I think it's time. Okay, so now we have our baseline data, 40 observations, 11 variables, and then we're just going to go ahead and look at age and ADA's COG and a correlation. And what we can see here is that there's a correlation of about 0.09. Now that doesn't really seem like much, but there might be a significant association, but we don't know just based off of the information that we've been given. So what we can do is we can run the core test function in order to be able to get an idea of whether there's a significant relationship. So in order to do that, we just go ahead and we're going to plug in those same variables once again. And as we can see here, just looking down at our console, we can see that there is a p-value of 0.05 or 0.58. So there's not a significant relationship between these two variables, and we can see the 95% confidence interval as well. So going from a correlation of negative 0.23 all the way up to 0.39. So that would suggest that there's no significant relationship. Okay. So in terms of trying to look at perhaps some visualization of this, one easy way to do this is to use the plot function. So we're just going to, again, call those same variables, and we're just going to do the same thing. And so that's going to run a plot, and then we can plot those variables. And as you see here, that our x-axis variable is going to be age, and our y-axis variable is going to be ADA's COG plus, and then just as, or ADA's COG. So just as a reminder, x would be the independent variable and ADA's COG would be the dependent variable, since we're saying that age predicts ADA's COG in this place, or in this case. Now we can also add some different things to this plot if we're so inclined. So for instance, if we would like to add a title to it, we can go ahead and we can just type in main equals, and then you can title it whatever you want. So I'm going to title this my first scatter plot. And now it's got a new title. But I can also change the names of the labels. So right now I've got it labeled as baseline $age. I don't really like that label. So let's just go ahead and let's change it to just age, since it might be a little bit confusing to somebody who's looking at this. And Y label, let's just relabel this ADA's COG total. And then this right here, changes the plot points to just a different design. So now we have it in black, and as you can see, we've changed our labels a little bit. So it's a little bit nicer to look at. Okay, but this might still not be enough for what we want to look at. So if I want, I can add some lines to my plot. So for instance, if I wanted to, I could add a vertical line by using the command, or by using the following commands. So all I would need to do is I just type in AB line, V equals mean, baseline, age. And what this is going to do is this is going to create a vertical line at the mean of baseline age. And as you can see here, that's right around 72, 73 years old. And I'm pretty sure that's accurate, but let's just go ahead and let's make sure just by going ahead into the data and typing in baseline age, and we see it's about 71, 72 years old. So that makes perfect sense then. Okay, next, let's just say that we want to make a horizontal line. So if I wanted to make an AB line at the horizontal, you guessed I put in H. Now let's just say I want to put it at a certain level that's not the mean of ADAS-Cog. Well, I can do this at, let's just say 10. So H of 10, I want to make it a different color. So I can make this green, for instance. And this is just going to create the length and the width of the line. So LTY, length, and then width. So line type and line width. So line type 2, you can play around with this if you want to see the different line types. And then the width is going to make it a little bit wider than the one that we had previously. So that's a nice little horizontal line that I have. But let's also say that I actually want to create a regression line. So I want to see what the correlation is between age and ADAS-Cog. So I'd like to see that nice diagonal line going through the data in terms of being able to understand what the relationship is between these two variables, because these horizontal and vertical lines don't really tell me too much. Well, the way I can do that is pretty simple as well. First, what I would do is I'm going to create this function called regline, and you can name it whatever you want. It doesn't really matter. There's no right or wrong way to name this, but I'm just calling this regline. And from here, I'm going to use my data that I have, and I'm going to predict ADAS-Cog from age using the baseline data set. So ADAS-Cog is going to be my dependent or Y variable, and age is my independent variable. So I'm using age to predict ADAS-Cog, okay? And this is from the baseline data set again. And so from here, what I'm going to do is I'm then going to use the AB line command, and then this time I'm just going to type in regline. And that's going to give me my regression line, my line that's showing what the relationship is between age and ADAS-Cog over my data set. And we can see it's not a very strong relationship based off of the data that we have. So we could also do this same function directly in the plot if I wanted to, but it's a little bit more work in terms of the code. So in order to do that, what I would do is I'm just going to type in AB line, and then I'm going to type in LM, and then from here I'm just going to do the same function that I had before. So I'm just going to go ahead and do this pretty quickly because I don't want to wait. And then from here I could maybe change the color. So let's just go ahead and let's just make this blue, for instance. And I want to make the type of line number 4, for instance, and I want the width to be super wide. Okay, and so from here we can see that it's a lot bigger now. It's a nice big thick line, but it's got all those dots through it going there as well. But let's just say that I also don't want to make that straight linear regression line, but I'd like to do something like a lowest curve. So that would be the squiggly line that shows the best fitting shape of the graph, regardless of whether it's linear or not. Well, to do that, I can just go ahead and I can type in lines, then lowest, and then I'm just going to do baseline age, baseline, ADAS-Cog, and then we're just going to type in, let's just say color equals red, and this is just going to give me a nice red line for the lowest graph. Oh, And so I didn't have the correct variable in. And as you can see, there it is. The lowest line is in there now. Okay, so there's also something else that we can do as well, and I'm just going to very, very briefly introduce this, and this is something called the scatter plot matrix. Scatter plot matrix is going to tell me where we can look at more scatter plots across multiple variables all at once. And to do this, you can just load the package lattice. And from here, we're just going to use the command splom baseline, and then we're just going to call the variables that we're interested in that we're interested in looking at the relationships of. So again, just as a reminder, if I type in the command call names for baseline, and I look at the variables I have, then variable 4, 9, 10, 11, those are the variables that I'm interested in for right now at least. So I'm interested in looking at the relationships of those variables with each other. And so for this command, I'm just going to type in 4, 9, 10, and 11. Oh, having some issues. Just give me 1 second. 4, 9, 10, 11. And then that's going to run. And then I can just see the lattices for the relationships between each of those variables. And this is just showing the scatter plots for each. I'm just looking to see if there's any relationship that's really interesting to me, or that I see a big clustering of, or something that's really sticking out to me. Another way I can look at this is I can also look at these data, and I can do so by grouping them. So for instance, I could look at whether the baseline, whether groups might have different relationships, and I can do that by just that's going to show me the different relationships for intervention group versus the control group, or whatever variable I'm interested in exploring. There's also other different ways of exploring these data. For instance, one might be the performance analytics package, and I'm just going to very, very quickly go through this. You can load this package if you want and play around with it a little bit, but this package also provides us with a lot more details about your data in particular. So once you've loaded the package, you can just go ahead and run these commands that I have here. And all this is going to do is it's just going to provide us with not only the correlations, but also a histogram. And it's also going to provide us with the correlations, as you can see right here, in a scatter plot. So it's a very nice way of looking at a detailed relationship for any variables of interest. The only downside to it is that it can get quite complicated quite fast. So you should probably only do this with a few variables at a time, or else it's going to be very, very hard to see everything on your charts. Okay, so next up, let's go ahead and let's go through some t-tests. So t-tests are where we're looking for differences between means. We're really just focusing on trying to understand whether there's a difference between groups for the most part in our data, but sometimes we're just interested in trying to understand whether a variable is different from 0. So the basic way that we could run a t-test is the one sample t-test. This is where we're just looking for differences from 0 for a variable of interest. So in this case, we're trying to see if age is different from 0. And as we can see here, yes, there's a significant difference from 0 for age. But more often than not, at least in health statistics, we're more interested in trying to see whether there are group differences or between group differences in a variable. So when we run a t-test, most of the time what we're doing is we're actually looking at group differences. So for instance, I may be looking at whether there's baseline differences in age by group. So in this instance, I can go ahead and I can look at the at this command right here, wherein I'm looking at group differences in age, and we can see that there's no significant difference between groups in terms of age. What I might also be interested in as well is I might also be interested in trying to look at differences in proportions that may exist between groups. And one way that I can do that is using the chi-square test, which is a way of just looking at proportional differences. And to do that, we just run the command x equal the chi.square.test, chi-square.test, and then x equals table of whatever it is you're interested in looking at. For right now, let's just focus on education and whether there are differences by group and education level. And what we can see here is that no, there's not differences between groups in terms of education level, that they have broadly the same level of education. And then lastly, what I'd like to share with you is just a brief introduction to ANOVA. So if you're already not familiar, ANOVA is a way that we can look at differences between groups wherein we can look at multiple groups, that is more than just one, or two groups. We can look at 3 or 4 groups or even more in terms of group differences. But we can also do a special type of ANOVA, which is the analysis of covariance, which allows us to adjust for different variables in terms of our attempt to look at different differences between groups. So let's just start with the basics. So to show you that there is no difference in terms of a t-test and a analysis of variance when we're just looking at group differences between two groups, let's just go ahead and let's just run a ANOVA wherein we are looking at the association of ADAS-COG by group at baseline. So for this, I'm just going to run the command lm ADAS-COG by group, and then just call this the data set of baseline. And then this is just going to create a function for that analysis of variance, and then I can just run ANOVA group.lm. And if you notice, the p-value and the difference between groups is going to be roughly the same. And you can't see it right now just based off of what I've shared with you, but f-value is actually just the square root of a t-test. So if I were to take the if I were to go ahead and run this t-test, I can show you mathematically that it's the same thing. So let's just take a look at that t-test. So t-test baseline ADAS-COG baseline group, and we can see that the t-value is 0.005096. Well, let's just see what would happen if I were to take that value and square it. So if I or I even better, I could take my baseline, my f-value, and I could take the square root of that. And broadly, that's about the same thing. So the point is that the math is the same, it's just a different test. So we're running basically the same thing that provides the same result. So a t-test and a ANOVA provide the same result when we're just looking at between group differences without adjusting for anything, and it's only between two groups. Okay, so the point is that all of this is the same mathematics. That's all I'm trying to get across to you for right now. Now, we'll talk a little bit more about ANOVA in a little bit, but for right now, what I'd like to focus on is let's just focus on a few more things that we can do using ANOVA. So for ANOVA, we can also provide a little bit more of looking at between group differences. So for instance, if I wanted to, let's just create a new data frame called education.lm. And from here, we're just going to look at ADAS-COG by group differences for education. And what we can see here is that there might be some differences between groups. And while there aren't in this case, we can also look at a little bit more of a summary in terms of the relationships between variables. So if you want, summary is a good command to call as well if you want a little bit more details about the ANOVA test in particular, and to provide you a little bit more details about the R-square and stuff like that. Okay, so next I'd like to focus in on talking about linear regression for just a little bit, as I think this will provide us with a little bit more detail. So We've talked right now about group differences, but we haven't talked about regression-based differences. And so here's what I mean by that. Is so far we've talked about a correlation, so age being associated with, with ADAS-Cog or something along those lines. But we can also look at the relationship between variables while adjusting for other things. And this would be a version of ANOVA or a version of linear regression. So let's focus first on the ANOVA, where we are going to do a ANOVA or an analysis of covariance. So in the analysis of covariance, what we are going to be doing is we're going to be adjusting for another variable. So let's just say, for instance, let's go back to that, we go back to this group differences in ADAS-Cog. Well, let's say that we think that age might actually be something that we need to account for in terms of looking at baseline differences between groups in terms of ADAS-Cog performance. Well, we can do that by just adding plus age, and that's going to help account for age within our results. And we should probably look at this both in terms of the summary and then also in terms of the ANOVA statistic as well. And so while there isn't a group difference in particular, we do see that we can start to add more things to the model over time if we were so inclined. So we could also add education as well, and then we can run the same result. And again, while there's no group differences, what these suggest is that there's no group differences in ADAS-Cog plus score after accounting for age and education level. So again, we can see that there's no group differences in ADAS-Cog after accounting for age and education level. Okay, next let's go ahead and let's just do an example of linear regression. So rather than trying to look at group differences, for instance, now let's just say that I was interested in trying to understand the relationship between age and ADAS-Cog after accounting for group and education level. So now what I'm doing is the question slightly changes. I'm asking whether there's an association between age and ADAS-Cog plus performance or ADAS-Cog performance after accounting for group, so intervention group, and education level. And what the interpretation of this would be is that there's no relationship between age and ADAS-Cog performance after accounting for group and education. But if we were to assume that this was significant, then that would mean that for every 1 year increase in age, we would expect a 0.09 increase in ADAS-Cog score, suggesting that they get slightly worse as they get older in terms of their ADAS-Cog score. So if you can see here, again, the point is that the math for all of these tests that we've done thus far is the same. We're using the same sort of basic mathematics in order to look at all of these individual things, whether it's linear regression, whether it's ANOVA, or whether it's ANCOVA, or whether it's correlation or t-tests or what have you. So with that being said, we're going to move a little bit forward now, and we're going to go into data visualization next.